Let's have a look at format level 4 from Exploit Exercises Protostar on a current Ubuntu machine. And this time I thought, instead of building the complete exploit from the ground up, we take the old exploit that we developed for the 32-bit Linux image and see if it still works. Probably it won't work, but then we debug it and slowly make it work on the 64-bit Ubuntu. Okay, so here is the source code again. We have a 512 byte large buffer on the stack, which is used to read data from standard input. But it only reads up to 512 bytes, so there's no buffer overflow. But then this buffer is passed directly to printf, so we have a format string exploit. Our goal is it to redirect code execution to the hello function. Notice how here after the printf we find an exit? Well, that was intentionally placed here because exit is part of libc, so there will be a global offset table entry for it, which we can override. Then when we call exit here, our overwritten function would be executed instead. So it's actually a pretty straightforward format string exploit. Just write to the exit GOT entry the address of hello and you are done. Hello and the GOT table have fixed addresses and are not affected by ASLR, at least on this Ubuntu version because of the default compiler options. I received several comments that wrote that on their system they default to PIE. So there the GOT address and the functions will be affected by ASLR, and then I don't think these simple cases are exploitable anymore. We would require a little bit more complex examples with more interactions where we first can leak values to defeat ASLR, but we will slowly get there over time. Let's not rush too quickly into these topics. So we compile this now on our Ubuntu machine and we get the old exploit code. Man, this was episode hex 13, August 2016. Holy shit, that is a long time ago. When I started, I thought I would have very quickly a complete series on all the basics, and we still haven't reached drop in ASLR. God damn it. Anyway, let's copy that Python code. Looks good. Now I write it into a file, exp, and then we can start GDB with format4 and execute it. Run, and then we pipe in the exp file as input to the program. We print a lot of characters that looks good, but we get a seg fault. We are attempting to write the value in R15, hex 84b4, to the address in RAX. And RAX is obviously wrong. Hex 58 is X. So this is the %n part of the exploit. Hex 84b4 is the amount of characters already printed. And it tried to write to the fourth value, and that turned out to be not the address anymore. So, two things. First of all, obviously the amount of characters that we are writing with %n are wrong. We don't even know yet what we want to write. And most importantly, we are not writing to the address we have specified in the exploit. Now with the format string offset, we hit our padding. Okay, so let's use this opportunity and get the correct addresses first. We need the address of the exit GOT entry. We do this by looking where it is called. Then we simply disassemble the few instructions that jump to the GOT entry. That's the PLT, the procedure linkage table. And here it references the exit GOT entry. You can see it will jump to whatever address is written there. So we have to overwrite this with the address of hello. And here's the address of hello. You can see again that only the last 2 bytes of the current exit GOT entry and our desired hello address are different, which means we only have to overwrite those last 2 bytes. So let's place these 2 new addresses in our exploit code, and we can also throw away the old format modifiers. And instead we just add a bunch of %p to find our new stack offset. So we write it again to a file, start GDB, and pipe the file in as input. No real output, just like an at and a backtick. Where are the addresses we leak with %p? These are the small things that can be really frustrating, and this actually happened to me when I was preparing this episode. I I was going crazy trying to understand what the heck is happening, and just executing it over and over again, hoping the computer would do something else. I'm debugging it to break before the printf and see that my input is passed to printf, but no output. God damn it, work. But it will not. If it's not doing what I want it to do, I made a mistake. I'm the problem. I need to calm down, take a step back, and try to figure out a way to figure out my stupid mistakes. So what exactly is the output we get? I pipe the exploit output into hexdump and see that it stops after 3 characters. And that is our address, but cut off. The other addresses and the format string is missing. But when I then also did the hexdump of the exploit, I noticed the obvious mistake. The address has a null byte, and printf stops at a null byte. Strings are null terminated. Goddamn, I'm so dumb. This was not an issue for the 32-bit exploit, because there our addresses had also 4 bytes and thus no null byte. Now on 64-bit, the default address is only 3 bytes, so our next step is we move the addresses at the end of our exploit. They still get placed on the stack with the null bytes. fgets will read null bytes. Just the printf format vulnerability part must not have a null byte. When we move it to the end, we want it to be at a fixed location. So we add padding to our format string and then make sure we have enough space for the 2 addresses at the end. We are on 64-bit, so we have 2 times 8 bytes, so we need 16 characters. Looks good. So we try that input into format4. Looks good, we print values now, but I can't find our addresses. Let's actually have a lot more %p. How about 100? That fits easily in the 512 bytes. Okay, so where are they? Here they are, but that doesn't look good. They should be 2 individual values. But it's pretty clear what happened. We forgot to also encode the addresses for 64-bit. Struct pack I packs an integer in 4 bytes, but we want it packed in 8 bytes. So let's try it again. Here they are. This looks good. Now let's find the offset. We can just count how much to the end and then subtract from 100. So at offset 68, we should find the address. And yes, indeed, there it is. So now we just have to print the correct amount of characters to write the 2 bytes. Actually, we don't need 2 writes. We should be able to do that in 1. So we add another format string with a padding of the amount of characters we want to write. That would be hex 676, minus the characters we already printed before, so basically minus 8. And then we should also remove the space before the %n. That would be another character printed. So it should work now, right? Segmentation fault. Damn. So when I was recording all of this, I really thought it should work right away. But then I get a segmentation fault. Really confused me. And that would be again something I could obsess about. Why did that happen? But after I stopped recording and literally started to write down what I just did in the script, I realized my mistake. When I wrote down %n, I realized I wrote a whole integer. But I meant to write only 2 bytes. So I would have required %hn. We should be able to verify this with GDB. Let's check it out. Yes, there it is. Seg fault at address 676. We wrote a whole integer. So we overwrote the higher bytes that were already stored in the GOT. So let's change it to hn. To write half a word or whatever that means. It writes 2 bytes. And that worked. Code execution redirected. You win. You see, the exploit is different from the original 32-bit version. It required quite some changes, but it also kinda still the same thing. Definitely not a hard challenge on a modern system, as long as you don't compile it with PIE.